Euclidean distance. So today we're going to allow more general clusters, so which can also be, for example, ellipses or other kind of shapes. So this is what we're going to do, and what that means mathematically is again coming from the shape of this distribution that we just discussed at a minute ago, right? Here we said that's why the whole model here was spherical for every cluster, because every cluster's distribution was a normal distribution, but with a identity covariance, right? So there was just a spherical Gaussian. So that's what you want to do now. Instead of the identity, have a more general covariance matrix. So that's what you're going to do. So just plug in this more generic probability distribution here, which is a real Gaussian, not a spherical one, so a general one, having these covariance parameter here as well. And the other thing is kind of the same, right? So the means, of course, they are as usual. We had this before already. So it's really the same expression as before, basically. Also, there is the assignment, and that's really again the same thing as before. So we again have an assignment random variable of how much or how likely is your one data point assigned to each of the k clusters. So the Zn is which cluster are you assigned, but that's a random variable as well. So so if you think of this motivation here again, then on the left side here we have that this sigma matrix, right, is the identity. So then we actually recover the k-means case on the left side, but on the right side we have the sigma matrix is general, by that I just mean any matrix, and then we have what we will have today, which is the more general Gaussian mixture model. So that's what we're going to do now. So if you look at the expression again, then we see the same model as before, except that the covariance has become more general, and now we want to understand this fully in a probabilistic model. So actually, what we're going to do is we're going to also assume that the assignment is kind of a soft assignment. So before we were always like there was a hard assignment. So every data point in the end was assigned in a discrete way for sure to the same cluster. There was no randomness to which cluster you are assigned. So now there will actually be randomness to which cluster you're assigned. And that's what you have on the last line on this slide. So here you see the Zn, which was just fixed before in k-means. So here it's going to be a random variable. So with some probability, you're going to be with that cluster, and with some probability, you'll be with another cluster. So that's a big difference here. And what this means here is that we have some kind of importance for each cluster. So not each cluster is equally important. They also might have different sizes in number of points assigned to them, or different importances. So if you think about this one number, which is like for all data points together, like what's the probability you're assigned to a cluster, then this importance here is called pi k. That's a number, a probability of the cluster k. And that number also is a parameter which we're gonna optimize. And we want that this importance to sum up to 1. That's just a technical condition here. So okay, so what is happening here? So we have a random variable z, and then we have this of course this normal distribution, and then so that was the first change, and then the second change is that z is also a random variable now. So these two changes are all that we did, and otherwise it's just k-means. So if we do this, then what it's actually going to happen is that you we don't know what these parameters are, right? We don't know what is the mu, we don't know what is the sigma, and we also don't know these pi importances, right, at the beginning. So there's like three kind of parameters. So the parameters are, I'm just making some statistics here. So the how many of each kind we have. So mu we have for every cluster, and what's the dimension of mu? So mu is in the same space as the data points. They're space D, but there are k many of them, so D times k. And then how many of these sigma parameters do we have? So sigma is a covariance matrix, so it's a square matrix. So that's in the D by D, which is D squared. And then also there is one for each cluster, so D squared times K. And finally, we have the pi parameters, so these cluster importances, which are only one number per cluster. So that's just K. So these are the three kinds of parameters we have. And we want to learn them. We don't know them a priori, so this is a little bit different from k-means. In k-means, basically, we only have this. But now we also have this kind of two new kinds of parameters. So the pi's and the sigmas and the mu's we always had them. Okay, so how do we learn them? So to do that, we first need to fully understand how this model now generates the data. So what's happening is that for each if you generate, you just need to ask, like, how can you generate one data point? So I want to generate the point x1. So that's I have many points, right? I have x2 up to xn data points which are generated, and for each point there's a few things I need to generate before. So first I actually need to generate this random variable z. Zn. So, and this is done very simply. So how we generate the z's is super simple. This just comes from this pi parameter here, and as you can see, it's a very simplifying assumption we did, right? So the probability that you are assigned to cluster K, it doesn't depend on anything, right? It just is pi K, like 20% for the first cluster and 30% for the other cluster, for example. So it's a very simplified model. So how you get this cluster assignment? So each n is independently, each data point n is getting this assignment completely independently from everyone else. So now you got your assignment. This is the random variable which came from this pi random process. And then you generate the x, but for that you also need to know a few more things, right? So now that you know which cluster you are, now you also need to use the mu's and sigmas for that cluster. So these also influence your data point, right? First, yeah, which kind of cluster are you from? Once you know that, then you take the mu from that cluster and the sigma from that cluster, and then you generate your data. So this is the full generative model. It's just this arrow notation is used in generative models. And what it actually means is nothing special. It just means that every arrow kind of means that some random variable has been generated when you see the arrow from the thing before, right? And this can also be interpreted. You can say that the thing which comes out of the arrow is conditioned on the thing at the beginning of the arrow. So this, we will see in a second that you can actually see this as conditioning. And what we want to do here is we just want to understand how is our data generated from this generative process. And as we will see, the kind of cool thing is that you will kind of have a soft assignment. So some points will be very clear which cluster they belong to. So this point here is only green. But there is also some points here which are a bit in a mixed territory. So this point here is kind of 50% with one cluster and 50% with another cluster. And that's the kind of new thing as well, where that's possible now. That's not possible in k-means. There you just either or. But here this is possible because where you assigned, that's the Z random variable, that can be 50% there, 50% there. So that's what the pi is allowing you to do. Okay, any question on this? So that's just the illustration. And then if you want this in formulas, this is also quite simple actually. What we just want to understand is, yeah, how does this model generate data? And that's exactly written here. So as always, we want to understand generating data X. How does that happen? From our parameters, the mu, the sigma, and the pi. And that's basically what we have done here, right? So how does this work? This is really simple. So again, like basically as we explained on the picture. So here you have the formula for this. You have that first the Z assignment is generated. So this is called the prior, but we will get to this. No, actually, let's look at this for 1 second. So this thing here is called the prior, because it will tell you the probability that you as one data point gets this following assignment Zn. So there is another thing here, and this you're also familiar with. So this is the probability of the data given the model. So, and that is called the likelihood, as we know. And then the whole expression on top. So that's the joint probability distribution of X and Z. So because the tricky thing here is that the X, of course, we have observed, it's here, right? But the interesting thing is that the Z's we don't observe, right? These are kind of mystery variables which are hidden. So that's what they actually called hidden variables or latent variables. So that's what's a bit confusing here, because the Z's are not observed. The X are observed. Maybe I use a different color. X is observed as usual. You see it. You got the data set. But then the funny thing is that the Z's, they are latent or unobserved variables. So, and we will see how we deal with that. But it's a bit funny that we don't observe them, right? So, okay, and what we have done here. So how did this come to be? Why was this equal? That this got this product here, and that is really simple. This is just it's just Bayes' rule. So because we're talking about probability of X and Z, so these are two things. The probability of these two things is P, A, and B. So that's the joint. And of course, with Bayes, you know that this is the same as P of A conditional on B, and then P of B. So, and that's really what's happened here. But you might be asking, so what about this additional conditioning stuff here? That does not matter at all, because this just means that there is a conditioning here on a few things, and that's actually, you're just going to keep this everywhere. So Bayes' rule still applies. If everything is conditioned on another random variable, that's fine, right? Then you're just talking about all the probabilistic things that can happen in that subspace, kind of, when in the space where we're conditioning on, we know what is the blue stuff. So that's these guys here, right? Sorry, Z, mu, and sigma, and pi. So that's what we conditioning on. Okay, so this is to explain the equation. And then here, of course, we just have plugged in the definition of a normal distribution, nothing special. And we have also plugged in the definition of how these latent sets being generated. That's just what we have in the last line here, right? That we defined that. We defined that these latent guys, they come from this super simple uniform probability pi k. Okay, that's the whole model. So that's what we have plugged in here. And then again, we have used these assignment variables, which you know is just a notation trick, basically. We have done the same in k-means. They are either 0 or 1, depending where you assign. So we use that to describe where you assign. And now the whole problem here becomes to maximize this likelihood. So that would be a good idea again, we guess. And we have to find all the parameters, right? These three kind of parameters, mu, sigma, and pi. And okay, actually I want to use a blue for my parameters. So okay, any questions on this, or so far so good? So three kinds of parameters. So. All right, yes. Yeah, why is this maximizing likelihood? Yeah, that's right. I haven't explained this yet. So we will get back to this. Like we will get to how also didn't tell you which algorithm we want to use it. Here, I just told you, okay, if this is my generative model for the data, then this mathematically is the likelihood, but I have not told you how to maximize it or why to maximize it. So we will get to that. Thank you. Any other comments? Okay, yeah. Yeah, you're talking about the sets ends, and you're right. I abuse notation a little bit here. You're right. The set here it's from 1 to k, right? But then on the next slide, you're right. I used set nk either 0 or 1. That's right. So yeah, I should. Let's make a little note. So this is just when I use both indices, then I mean that set nk is the expansion of that, right? So 0, 1, set nk, or whatever. Or set n here is written as this 0, 0, 0, 1. So this one hot vector, which has the 1 at position k. Position k. So, but it's the same thing, yeah. So it's just it's always representing this number from 1 to k where you assign to, and that's so z and k is this, yeah, either 0 or 1. Okay. Hope this is okay. Okay, so we defined the probabilistic model, but we have not talked about yet how to maximize likelihood or how to find the best parameters. So now we need to talk a bit about that. And to do that, we need to get rid of these latent variables, because the big problem we have here is that the z's, we have no idea what they are, except that they are 0, 1s, right? But we don't know which cluster you are, and we don't know with which probability. So we don't observe these z's. This is a problem. So we want to get rid of them. So and this is not so obvious, but what you can do is the nice thing is about having probabilities is that, so this is what we looked at before, right? The probability of both together, the joint. So X and Z. So I write the N as well. X and Z. And again, here I mean the Z, the full expansion. So this is the joint, but the problem was that we don't observe the Z's. So, but what we can do is to get rid of it, we can just integrate out the Z's, or that's what's called marginalization. So that means that you just kind of ignore Z. No matter what Z is, it's from a random process, right? So you can say, I will just ignore the outcome of Z and consider the probability only of X. So, and that's called a marginal, right? So that's what just P of X is, right? So, and of course you can always consider these terms, right? The question is, how are they related, right? So, and it's not hard to see how they are related, right? Because you can just, if you know that this, whatever X is, right, it could be coming from many possibilities of Z, and it's very easy to compute this, right? You just need to sum up whatever cases can happen, right? So it's just the probability of X for all possible cases of Z. So Zn equal to K, and then I'm summing up of all possibilities of K, right? So this is just a definition of this probability. Whatever can happen, I will just sum it up. and that you can have, again, apply Bayes rules if you want here. So so that you have the condition probability of X and Z times the probability of Z. And now this looks a bit more convenient. So this actually is pi k. We defined this way, right? So we defined the random process to generate these Z's in this way. And this again was just by Bayes rules. So. Okay. So the idea is, if I don't know these Z's, I will just ignore them. I will pretend that they never existed. And that's what we have done here, right? So instead of considering the joint, just consider the marginal with only looking at X. So, all right. So you can do this for the probability. Then of course you can also do it for the likelihood. So we had the original likelihood as we had on the previous slide. So the original likelihood, or just whatever likelihood is. If we go back, then we had that, well, I don't need the specific formula. I will just say that it was the X and Z, right? X, Z, depending on the parameters. So parameters, this theta includes all parameters, right? All three kinds. So here are the three kinds of parameters, right? So this is the likelihood of getting X and Z given the parameters. So this is what it truly is, right? But now, can we do the same thing here? Can we just ignore the Z's and talk about only the X? And that's yes, you can do that, and that's what's called the marginal likelihood. So you just take the same thing, but you have ignored the Z's. How do you obtain it? Of course, again, you just sum up all possible cases. So this thing here is, as we have done on the top right, we have just summed up whatever the set can be. We have summed it up, and then what remained here is the pi k for a cluster K. So this is the marginal likelihood if every in a Gaussian mixture model, where everyone comes from a Gaussian around this cluster center mu and this covariance sigma. It's exactly what we had defined here. This is the model to generate our data with these unknown z's. And here is the same model if we have marginalized out the z's. If you don't know them, we have just summed up all possible outcomes and get the overall probability if you don't know what really particularly happened to each set. So, and why is this good? So that is a bit unclear here, right? But it's really because you don't observe the set, so you can also not optimize them and find them. That's why we did this. So, and also there is another small issue about the number of parameters we have, right? Because if you look at this model here, so this one looks kind of nice, right? We only, when we want to maximize the likelihood, so assume that's what you want to do. So we have convinced ourselves this is the likelihood. Let's assume we want to maximize it. So what do we need to do? Need to optimize this thing for all the 3 parameters. This looks doable, right? There's only these variables here, right? But in the original one on the previous slide, this was horrible, right? There were so many unknown things. There were all these parameters, and there were also these unknowns z, which you cannot deal with. So now we have solved that problem by just looking at the marginal likelihood. So this one is easier to optimize because it only has is only based on observed things, and also it has fewer parameters. So in the old models, if you also include the z's, then in the old model you had a growing number of parameters, right? Because for each data point n, there was its set assignment. And if you also want to optimize those, so if you say my z's are also parameters, then this is really hard. So then there's lots of them, and the problem is more complicated. Specifically, if huge data sets, then the number of parameters in the old model here depends on n, and in the new model here, the number of parameters I have is not depending on n. So that's kind of nice. So set how many of these are. So this is order of n. I ignore the k here. And then the sigma guys, is much fewer of those, right? So there was the mu, the sigma, and the pi. And none of this depends on n. This was k times d squared, k. So none of this depends on n, which is nice. So we have, after the marginalization, we seem to have a problem which is a bit more tractable. That's the takeaway here. And how should we think of this intuitively? What does this marginal, what does this change? The only thing it changes is like going from here to here. So on the left, you see, if you know for each point where it's assigned to, right? So that's why there's the color. So for each point, you also have its set, its assignment. So that's why you know the colors on the left. If you do the marginal here, there's no set anymore. So you don't know anymore which specific data point belongs to which cluster. You just want to fit these blue parameters such that they maximize this likelihood here, which is not depending on the sets anymore. So we're just trying to kind of find the best parameters for this. Okay, specifically important when you have lots and lots of data points. Any question on this? So. Okay. If not, we can briefly talk about how we would now do this. So, I mean, how would we find these parameters, these 3 types of parameters now, such that they best explain the data that we observed, which means, so that's That's these 3 types of data, sorry, the 3 types of parameters, right? Mu, sigma, and pi. And so how do we find those such that you optimize the likelihood? So this thing here, the whole expression here is the marginal likelihood, and I'll explain you again. So because before we only talked about like 1 data point here, so I need to be a bit more careful what really happens when you have several data points, and that's what we're gonna have a quick look now. So forget about this crazy formula now. So I will derive it first. So what we want is we want to understand the probability of all the data points together happening, right? So you can just write capital X for this, or I write all small xn given the parameters, right? This is the marginal likelihood. And what it is, of course, every data point has been drawn independently from the same process. So therefore, it's a product of over n, the data points, of the probability of one of the points happening. So the likelihood of 1 data point. And what is the probability of this 1 data point? This we have seen on the previous slide, actually. So if you go back here, then that's exactly the expression we have here. 1 data point given our current parameters. What is it? It's the sum of this normal distribution, what they get mixed together. That's why it's called a mixture model. And the mixing weights are these fixed numbers pi, right? So pi is just this importance for each cluster. And that's the weight you give to each of those clusters or normal distributions for each cluster. And so let's plug in. So sorry. So I want to take this p of x and plug it in here. So sum over pi k of the normal distribution of x around the k's cluster mean, mu k, sigma k. And the sum is over k. That's nice, but now this looks a bit nasty. So we have a product and we have a sum. So maybe what we can do is we can take the log of everything, then things will simplify. So the log of everything is the sum over the data points now, 1 to n. So what I've done here is just the log of a product is the sum of the logs. So that's what's happening. That's what has happened so far. So now I just need to copy paste again this p of x, which is again the sum over k of these normal distributions. And this formula here is exactly what we have here. So that's why the marginal likelihood has this strange structure where there are 2 sums. And the extreme thing here is that there's this is special structure that there's actually a log between the sums, which is quite nasty in a way, right? It means that the sums don't really have the same effect, right? It's not that they can be treated the same way because they influence things very differently. But now this, I think, finalizes our discussion, what we want to optimize here. So now we know that we really want to find these parameters theta, which maximize this. And this seems not an easy problem. So we will discuss a little bit why this is not an easy problem now. But is it clear that this is the marginal likelihood now? if you have this model where with a mixture of k Gaussians. So if that's okay, then maybe we will take a short break, and then after the break I will explain a bit more why this is a difficult problem and how we can solve it and find the solution. So see you again in 15 minutes. Yeah, here. So the question was on these three guys, right? We were conditioning everything on the same thing. So that's this additional conditioning, and that was that's these pi's and mu's and sigma. So why is it not the same in left and right, right? So here there's only mu and sigma, and here there's only pi. So, but the point is actually to be precise. All three of them are present in both. So actually also here on the left you would have mu, sigma, and pi, and also on the right you have mu and sigma and pi. So these are all three on both sides. But the thing here just does not depend on mu and sigma at all. And also here does not depend on pi. That's why it disappeared again. But all three are present in all terms actually. So that I should have maybe clarified. Okay. Then, so now we had the marginal likelihood for the whole model when all the points are generated, right? So not only one xn, but all of them. And that was the expression we got. It looks a bit nasty, and it actually is. So to actually maximize this cost function here, it's not good to maximize cost. That's not a smart idea. So, but you would say this is like minus your cost function or whatever. That's maximizing the likelihood or minimizing the cost. So that's what they're doing here, trying to find these parameters theta. And okay, what are the problems here? So a bit similar in k-means. So in k-means we also said that some things are not so easy. So actually some parts were tricky in k-means because it's also a non-convex formulation here. So that is one problem. Actually, maybe I'll show you 1 second here. So why is the k-means also a non-convex problem? So we can actually maybe let's take it from here. When we look at k-means, and we had a very similar expression here, but there was no latent variables here. And then we said maximizing the likelihood in k-means was just solving this thing here. And so that's the L I was just talking about. And we said in k-means it's a bit easier to understand and what the optimization function looks like. And what it actually is I forgot to say this last time, this is actually a matrix factorization. It has a nice, easy expression for k-means. So there we were optimizing something a bit different, right? We were optimizing mu's and z's, which had the z's had a very different role there. And they were integer variables, which we optimized, right? And today it's different. Today we make them probabilistic, and we made them latent variables, and we made them disappear. So it's very different from the k-means case. But the k-means objective function is why I bring up this slide again here, is because this is actually a matrix factorization, because we said we will just that is the likelihood, and we are maximizing it, which is the same as minimizing the cost function here. Remember here, so this is minus the log likelihood. That's the L. So that's what we are minimizing here. And what is it? It's actually the data matrix minus the matrix which collects all the means. And then the Z matrix is this assignment matrix, which is 0, 1 in this case, which is a bit harder to optimize here. What I want to say here is that it's a product of two matrices. So and when we have a product of two matrices, then then that's already kind of an indication that things are a bit difficult to optimize, because it means it's a bit like a saddle function, right? When you have two variables, you multiply the two variables, then that's a bit like a saddle function, which means it's not a convex function. We discussed this in week 3 when we talked about optimization. Then, so this is actually a difficult objective function on one hand because it's a non-convex function, because it has this saddle shape. If you just look at the inner function here, I mean x is constant, right? And these guys are behaving. The landscape of that part is like a saddle, and then outside we have just a square norm, which does nothing bad. But the problem is that the thing in the inner loop, inner side, is already a difficult objective. So, and let's compare this to what we have now. So now today we have a Gaussian mixture model. The objective function looks a bit more complicated, but what I want to say here is that it's actually also a non-convex problem. So it's not convex. So let's list a bit what the problems we have. So first, it's a non-convex problem. Second, so I'm not going to prove that it's non-convex, but you have to believe me at this stage, and maybe you can convince yourself if you would plug in the definition of the normal distribution, then you would have a very similar expression as we just had before for the k-means case. So the second problem, that it's not identifiable. So, and by identifiable I mean that there's some optimum, but then there's might be other completely different optima. So it's not that this one unique optimum. So non-unique optima. So why is that? So assume someone gives you one optimum solution to this problem, which means it gives you all the blue stuff, which is the pi's, the mu's, and the sigmas. Do you have some suggestion on, could you take that solution, so it's 1 point, mu, pi, and sigma, could you take that and generate another solution, which is a different point, but is an equally good value in this problem? Do you see some kind of symmetry like this, that there's many solutions if you are given just one solution? So any ideas? Yeah. Yes, you switch between the first and the second cluster. You switch the mu's and the sigmas. What about the pi's? Yeah, you're right. That's one way to get a symmetry. But if you have a general pi's, then you would also switch them. You just switch everything. But you're right. So you have a solution, and then you would just switch which group is which, right? So you were suggesting we switch the first two groups. That's right. And in general, I will just switch everything from these two groups. Yes. So the three variables. So you switch from, you had whatever was group K is now gonna be switched with group K prime. So the pi's are switched. The sigmas are switched. And also what's the last one? The means. Sorry, I'm mixing up the order of these. The means, the sigmas, and the pi's, everything is switched between two groups. So then this is the way to find another optimum, which is good, and you can do this much more. You can have all kinds of permutations of the groups, right? You can you can completely reshuffle which group is which. So you take a permutation of all groups 1 to k. So this angular bracket k here means all the numbers from 1 to k. You take a permutation of that, and then that's how you reassign your variables. So it just means you have changed a few coordinates of your variables. But the point is, of course, switching the names of the groups does not change the value here, right? Whatever objective value you had in the current group k now will be switched to the group k prime. So it sums up to the same thing. So any permutation will lead to the same value. Yeah. Question. What condition do you mean? Yeah, if you have additional information about what some of the groups are, then there might be more or less of these symmetries. Yeah, or maybe two groups have the same parameters anyway, then this would change nothing. So yeah, this assumes that every group is a bit different, and then you do have at least n factorial, sorry, at least k factorial many other points with the same value. There might be more, there might be less. That's not so important. The point is there is more than one solution. So that's what you want to say here, that it's not, in statistics you would usually like to have, that's what you call by identifiable, right? That there is one model which explains the data. So that's not the case here. There's at least two, maybe there's k factorial ones which explain the data. So that's also, so it's not so, I think this is, of these three problems here, this is the least severe problem. So it's quite common that you have symmetries in your problem. Also in neural networks, it's very common to have, if you change some neurons, change them with each other, they take each other's role, then you also have symmetries like this. So it's very common to have several optimal solution in machine learning problems, so machine learning optimization problems. So that's not so uncommon. What is a bit more problematic here is the third problem, that it's actually not bounded. And with that, I mean that this objective function we're trying to maximize, it can become unbounded. It can become extremely high. And that is a problem. So the loss, well, okay. So the L is the likelihood can go to infinity. Sorry, L is minus the likelihood. So minus L can go to infinity. So and why is this? So the problem here is that when these Gaussians become, so here you have one group which is on the right. So you have a mu2, and then you have another group which has a mean mu1. So kind of two groups. So there's these two Gaussians which are added to each other. And the question is, how wide are these Gaussians? And that's taken care of by the sigma. So the width of this Gaussian is kind of sigma is the width. And so yeah, if in the general case, this is the capital sigma, right? So the question is, when one group becomes so small that it only includes one point, then the point is that then you can make this, the Gaussian of that group can become extremely small. It's still perfectly fine to explain your data point, but it can become extremely narrow. And when that happens, the value of this cost function will explode. So that it will become like a Dirac in this probability distribution. So what you have in the plot here is not the cost function, it's the probability distribution over your space X, right? So where is the most probability mass? Where are the most points happening? So the data points are the blue points. So where are they happening, right? And how likely? So that's what's shown here. And of course, that's defined by the sum of these Gaussians. It's the same picture as we had here. So that's the picture. So in this picture, if a group just becomes only containing one point, I mean, containing is a bit a soft term here, right? So there was always might be a small chance you assign to some cluster and some other probability with another cluster. But if a cluster really becomes only consisting of one point, and that point becomes with probability almost 1 to that cluster, then the cost here goes to infinity, because the logarithm will make this explode actually. So this is a problem that can happen here, and you can see this when you plug in the definition of the Gaussian here, right? When it becomes, the width is encoded in the sigma. So you will see if you when you plug in the definition of the natural Gaussian distribution, then you see that it's kind of normalized with 1 over sigma, right? If this width becomes super small, then the value can become arbitrarily high. So that's the problem here. So if the covariance matrix is, the shape doesn't matter, right? You already get this when you have identity covariance, but then you have the sigma, the scalar variable, which tells you how big is this spherical cluster. If that becomes small, so here's the width, then the cost function will explode. It will go to infinity. So it's just parameterized by some width, and this width becomes very small. So width goes to 0. Then you have that this happens. Okay. This is all I wanted to say here. So this is kind of 3 reasons why maximizing this likelihood is not so easy, but we will actually see very natural algorithm now, and then more on Thursday, how to solve problems like this. And by solve, I don't mean to perfectly find the true optimizer, but these are very good and established learning algorithms to find good solutions here, and they're very natural. They also have this alternating fashion. So like in k-means, you first try to get a good assignment, and then you try to get a good expectation here. So we will get to that. Yeah, one more question was there. Yeah, so I mean that the likelihood goes to infinity. So you're asking why is the minus, right? So the likelihood will go to infinity. That's the problem, I mean. So, but when we say maximizing likelihood is like minimizing some cost, well, it doesn't really matter. Actually, you can skip the minus if you want. You can say L is the likelihood, because we don't care what the cost is here. We only talk about the likelihood, and that we maximize, of course. So maximizing the likelihood, and that thing will go to infinity. So that's, if you have a maximization problem and the objective can become arbitrarily large, then you have a problem, right? Then, so then it's not clear if the solution even exists, right? Or if it might just grow completely unbounded. Okay. Other questions? Yes. Yes. The same value of this function, right? Yeah. So your question is just about the permutation, right? From 1 to k, and you're right that when I switch to when I switch the IDs or the names of these groups, that's what I'm doing here, then you're right that the function value, it does not change at all. So the value of this thing remains the same, right? So that's the same optimum value, but the points where we obtain it, the blue parameters, they change, right? That's what I mean. So, and the optimum, when we talk about an optimum, that's the blue point, right? And the optimum value, that would be the function, which I agree with you is unchanged, right? But the parameter itself, where the optimum is attained, that has changed. So, thanks. Yeah. Yeah, how can we maximize the likelihood? Yes, I will get to this. That's exactly what we're going to do here with this very generic algorithm. So this algorithm here can be used for many problems, not only for this mixture model, for many more things. This will be a very, as I was trying to mention, will be a very generic algorithm to have these alternating kind of steps between two types of steps, a bit like in k-means, and this one will allow you to solve any problems like the one we just had. Yeah, maybe not solve provably, but to get to very good approximate solutions. So that's, I will just start this, and then we will finish it on Thursday. What's really happening here with the expectation minimization, expectation and maximization algorithm. So these are the two kinds of steps. So, and the motivation is really what we just had, which is exactly this expression here. We said it's kind of hard to directly optimize this thing. So we would like to actually optimize something a bit simpler, right? So this was very non-trivial. So is there a way to simplify this objective function and kind of step by step approach it, try to solve a simpler function in each step? That's kind of what we would like to do. So the full objective function would be something like this. So it's a non-convex function, right? So I draw something like this. So this is my entire objective L. I want to maximize this thing, and okay, maybe I shouldn't. Maybe there should be some maximum point here somewhere. So, and what I'm trying to do is to find surrogate models wherever we are, so to simplify this job. So let's assume we start somewhere at some guess, right? So this is an iterative algorithm. We just start with a starting point theta. I call it theta t for time step t. So now I'm here, and the green function is much too complex to optimize. So I'm trying to find something simpler to maximize. A bit similar. The simplest thing you could do is maybe a linear approximation of this model. But here we will take something a little bit more advanced. So we will get to this. But you can imagine it's a much simpler model, like maybe some kind of parabola, or a simpler thing, which hopefully is a bit related to the green objective. And then we maximize that surrogate model. So let's say here is the highest point of that surrogate model, and that's our new iterate. So that's the point theta t plus 1. So that's my next point. So I will go here, and now I build a new surrogate model. So now I look at my actual objective, the blue one. So it's different from where I am. So then I will again build a surrogate model there, which brings me somewhere else. So maybe brings me here, and that's my next time step, right? And so on, and then again, you continue this forever. You always try to find the highest point of this surrogate model, and then there build a new surrogate model and do it again. So this is the idea. And what you'd like to go is to this true maximizer theta star. So we cannot do that. So we just try to go somewhere close, and this is an iterative process, trying to improve this step by step. And this, so the green function is called L, and the surrogate models, we also give them some names. So the surrogate thing will be, I will call it whatever, also L, but it's this special L. It's defined, it's also a function of theta, but it's defined at theta times t. And that I will call it L with a small bar under it to say that this is actually a lower bound to the green function. So that is the surrogate. So, and the definition will come in a second. So it's important that there is a different surrogate depending on where you are, right? This is the one when we are at theta t, right? So that's why there's a theta t here. So that's where you define your surrogate. So they will have the property that they are below the function. So that property is written here. And they will also have the property that they do coincide with your function if you ask at the current point where you built it. So that means that here they are touching, right? So they are identical in the objective value. So these are two properties, and I will tell you in a second how to build these surrogates. There's of course many ways to do it, but then first we want to understand the algorithm, and that I think is clear now, right? So we have the surrogate. So you define your L bar. So this is L bar, and then once you have it, you maximize it. So that's kind of taking this argmax of the L bar, and then that's your new point, right? Once you have done that, you move to your next iterate. So does this make sense? It's a bit confusing that the L has like two parameters, right? The one on the right side is where it is defined. So the yellow thing is fixed here. And then the parameter here is just, because it's also a function, right? So wherever you ask this function to evaluate it, you have to ask somewhere. So L bar has this kind of two arguments, but only the first one is the real function argument. The second one is just where it is defined. So, all right. So to define this, actually, there's a small competition to do, but this will be a very natural choice when we will use the property of the logarithm of being concave. So that's how we're gonna, what we're kind of doing is the problem is this logarithm in the middle, right? It's a very non-linear function. If this logarithm would not be there, then life would be completely easy. But this logarithm makes it very difficult to treat these two sums, right? It's very tricky. So if you can replace the logarithm by something linear, then life will be much easier. And that's what we're gonna do. So we're gonna say, okay, the logarithm is a nice function, a concave function, and by that we will be able to replace it by a linear thing. And the linear thing, if you have a concave function, which means curve to the bottom, you have that the linear is always below the original function. That's what it means to be concave, which is the opposite of convex. So that you're always below, and that's what you have here. That's why how we're gonna prove this, that we can show that our surrogate, because we have used that, is gonna be below the green original function, right? So that's what we're gonna do, and then this will be easy to show that they are equal at where you defined it. And once we have that, then we will also see that actually the surrogate L bar is much, much easier to optimize. And then we will have the algorithm for this. And this I will do on Thursday. We can finish a bit earlier today. So if there's no question, then okay, then see you on Thursday. So.